Hi. Testing, testing. All right, welcome to the recording. Here's the problem that we're going to be working on today. So we're going to assume that we have this, we're a business, and our business is to manufacture thermometers. And we hope that when it's freezing outside, the reading on our thermometer is 0 degrees Celsius. That means that the thermometer is working correctly. But, you know, we don't have to have them exactly correct. There's a standard deviation of 1 degree. So, you know, some of our thermometers are going to be off by a degree or two, and usually that's not the end of the world, assuming these aren't like medical thermometers or something. So anyway, so that's our factory. Here's how we're working. But we don't want to have our thermometers to be off by too much. So what we do is after we produce them all, we test them, and we're going to throw out the 2.7% of thermometers that have readings that are too high, and the 2.7% that have readings that are too low. So we're kind of getting, if a thermometer's not working, it might either be telling us the temperature is higher than it really is or lower than it really is, and we want to get rid of kind of the worst offenders in both directions. So the question is, if you have, this is your factory, you need to figure out which are the worst ones, so you need to come up with a cutoff reading. So if it's really 0 degrees out, if your calculator says it's 2 degrees out, is that enough to throw it out, or are you only going to throw it out if it says it's 5 degrees outside? So we're going to figure out what those cutoff values are. So let's begin here by drawing a picture. Pull up our whiteboard, draw a picture. And I always like to begin any of these normal distribution problems by just writing the given information. So we're dealing with a normal distribution here, and our mean, the mean reading on those thermometers is 0, and the standard deviation is 1. And now we want to sketch in our normal curve. Let's see if I can get a straight line to start us out with. There's a straight line as the base of my normal curve, and now let's draw that normal curve in. That's a little bit harder to do with a mouse on the computer, but let's take our time and try to make a really nice one. Oh, I hope yours looks better than mine. You know, it's good. It should be symmetric, but there's our peak, our 2 inflection points, and let's go ahead and label the mean of that normal curve is at 0. Okay, and we don't always have to label the standard deviations as long as we've written it somewhere in our given information up there. Okay, so now let's go ahead and fill in the values of interest. They want to know, what are the 2.7% thermometers that are too hot? So I want to think about that number 2.7% and think, is that an area under the curve, or is it a value on the horizontal axis? And the key piece of information that I can see there is that it's a percentage. It's a percent of all the thermometers made. So that's telling me that 2.7% is an area. So I can say 2.7% is a very small area, so I want to go pretty far out on my curve and shade in the area above it and say this right here, this area that I just drawn in red, represents the 2.7% with the highest reading. So I could write it as a percent like that, or you could convert it to a decimal, which is often more helpful. If this were a decimal, we would write it as 0.027. And then the other thing I want to do is label the same thing on the other side. We're going to get rid of the 2.7% of thermometers with the lowest scores. So here's my other 2.7% down here, and we can fill that in with the decimal, 0.027. And now we can think about what are the numbers we're looking for here when we solve this problem. We're looking for the numbers on the horizontal axis. We want to know, what's the reading on that calculator? If it's freezing outside, if the temperature is really 0, what is this calculator going to say? And what are these calculators going to say? Something greater than that number. Alright, so now we can think about which calculator command do we need to use to find those answers. And our options are normal CDF or inverse norm. And here, in this situation, we're given an area or percentage, and we want to find the value on the horizontal axis. So that's the situation where inverse norm is going to get us what we need. So we're going to use the inverse norm command. The inverse norm command. When we do inverse norm, the first thing we enter is always the area to the left of the value of interest. So if we're looking for this question mark here, The area to the left of that question mark is 0.027, so that's the first thing we enter there. And the next things we enter are the mean, which was 0, and the standard deviation, which is 1. So let's go ahead and put that in our calculator and see what we've got. So we do second vars, and then option 3 is inverse norm, and we do 0.027, and then mean 0, standard deviation 1, and the number I'm getting there is negative 1.9268, so we could round that. So let me write it in here. So we're getting negative 1.92. If we round there, it's going to be 68. Yep, 68. The next digit is 3, so we round to 8. So that tells me this number right here was negative 1.9268. Now, to answer this question in WAMAP, they're not just asking for this value. This is the one value they want, which tells us, okay, when I look at that thermometer, if it's 0 degrees outside, if that thermometer says anything less than negative 1.9 degrees, I'm throwing it out. I can't sell it. And similarly, to be in the top 2.7%, now we want to know, okay, well, what value has to be here? So we could use what we know about the symmetry of the normal distribution, and we could say, well, 0's in the middle, then this has to be symmetric to this. This value is going to be the positive of that. It's going to be 1.9268. So we can use symmetry to get it, or we could use the inverse norm command to calculate it, just to check our work there. So we could use inverse norm to get it. When we do that, though, we need to be really careful about what we enter as our percent, because remember, inverse norm always wants the area to the left. So we have to think about, well, if this area is 0.27, the area from here all the way over to the other side is what we would enter there, and that's going to be 1 minus 0.027, which is, let's make sure we get it right, 1 minus 0.027 is 0.973. So we can verify this answer here by doing an inverse norm with 0.973, meaning there's 97.3 area to the left, or 2.7 to the right, and then our mean and the standard deviation are still the same, 0 and 1. So we can put all that in our calculator. We use the inverse norm command, so second vars, and then choose option 3, inverse norm, and then we've got 0.973. Oh, not a negative. I wrote a negative. 0.973, and then 0, and then 1, and it gives us 1.9268. So that same answer, we could calculate it either way there. And then the last thing I want to check on this problem is, how did WAMAP want me to enter the answer? So we got our answers there, 1.9268 and negative 1.9268. Let's go back and look at that question for a minute. See if I can let WAMAP will let me do that. Okay. And it said the solution as an interval. So we can use parentheses here to show our answer and a comma. So the way I would type it in is I would do comma, negative 1.9268, like that, and then a comma, and then positive 1.9268, and then close those parentheses, and that should give me the correct answer.